So let's talk about Leetcode 1192, critical connections in the network. So first, let's draw a example network. We have node 1 connects to node 2, node 2 connects to node 3, and node 1 connects to node 3. And we have another node, node 0, that is only connected to node 3. So in this network, the critical path is the edge that's connecting 0 to 3. So why it is the critical path? So when you remove this edge, the node 0 can no longer reach any node in this network, and you are basically breaking this network into two subnetworks. So to solve this problem, we use DFS starting from any random node in this network. And while doing the DFS, we keep track of two numbers. One is the depth of the current node. The other number is the min depth of the current node. So the min depth is basically the smallest depth of any node that is reachable from the current node, and we will show what that means. So let's say we start from node 1 here. At node 1, we have depth of 1 and the min depth of 1 also. Note that if you visit an unvisited node, the minimum depth is always the depth itself. And let's say we search from smaller to larger numbers. So from node 1, we go to node 2. And node 2 will have this depth of 2 and min depth of 2. And node 2 will go to node 3. At node 3, we have 3 as depth and min depth as 3 again, and etc. At node 0, we found out that there's no other nodes to visit, so we backtrack to node 3. And the key thing to note here is that at node 3, we find out that the min depth of node 1 is smaller than the min depth of node 3. So what we do here is we update the min depth of 3 to be 1, and we backtrack to node 2. Similarly, at node 2, we find the min depth of node 3 is smaller than the min depth of node 2. And we do the same thing, we update the min depth of node 2 to be 1. So at the end of the DFS, we maintained the depth and min depth of every node. So if we put that into a table, so what we observed here is that node 1 to 3, they all have the same min depth. And node 0 has min depth of 4. So we observe that only node 0 and node 1 has their depth equal to the min depth. Going back to the network, we can actually see that node 0 and node 1, they are actually the entry point of a strongly connected component, SCC. So SCC is basically a directed graph where any pair of nodes can reach each other. So in this network, we observed two SCCs after we did the depth first search. One SCC is formed by node 1, 2, 3. The other is formed by node 0. So as we can see, node 1, 2, 3, any node, 1 can reach 2, 2 can reach 3, and 3 can reach 1. And for node 0, it cannot reach any other nodes. And the edges that connect the SCCs into a whole network is actually the edges we want to find, which is again called the critical connection. So let's transform this concept into code. So here we define the critical connections function. The input is n is the number of nodes, and we pass along all the edges. So the first step we do is to convert all the edges into a graph. Since we know all the nodes are from 0 to n minus 1, therefore we can use a vector to store the adjacent node of any given node. And we define another vector called min depth, which is used to store the minimum depth of any node that is reachable from the current node. And the initial depth is 1, and we always start from node index of 0, although any node can be used as the root node here. So in this DFS function, we first initialize the min depth with the current depth, as we discussed before, and we get all the adjacent node of the current node. So note here, we also use the min depth to denote if a node has been visited before, as the min depths are initialized to be 0, and if the min depth value is 0, it means the node has never been visited. So we recursively call the DFS function. And while doing the DFS, we want to keep the min depth value of the current node updated by comparing with its adjacent node, except for its parent node. Eventually, if the min depth value of the node equals to the depth value, it means the node itself is an entry node of a new strongly connected component, or SCC. In that case, we want to add that edge into the output. So in summary, in this problem, we use depth first search, essentially turning the undirected network into a directed graph. And by keeping track of the depth and the minimum depth of each node, we can effectively detect strongly connected components. We can also identify any new entry point of a strongly connected component, which would let us to get all the critical connections in this network.